And well, of course, we were working with some problems with some exercises for parametric equations. Let's do one more. So let's sketch the curve represented by this set of parametric equations and write it in rectangular form. Of course, that means we need to eliminate the parameter. So let's see. How about we just go to our graphing calculator and type our function 1 plus 5 cosine, and in this case be careful, it's 2 theta or 2t, and the second equation 3 minus 4 sine. (2t), close parentheses, and let's see the graph. And well, in this case what we got, it's hopefully you didn't blink at the moment where we plotted the function, and it went counterclockwise, right? It went counterclockwise, and well, that looks like an ellipse to me. So this is what we're going to do. We're going to eliminate the parameter, and we are going to obtain the ellipse not in parametric form, but I mean in rectangular form. All right, so let me know if you're having issues with getting this graph for whatever reason. All right, so just make sure that for this particular example your settings on the window look like this. Okay, so let's graph, and yes, it's going to go clockwise. All right, and well, let's go back to the algebraic part. For the algebraic part, so that means, well, the interval in this case would be from 0 to pi. And well, from the two equations, well, number one, let's draw the graph, of course, by hand. Yes.
When I change right now that you were changing the window, it regraphed it vertically.
It graphed it vertically. Okay, what are your X and Y settings? So window. So
I copied the same as yours.
You copied the same as mine? Okay, let me have a look. And well, so let's write down the equation of the graph, right? The graph first. And it sort of looks like this. All right, and it's going to go in this direction, or rather in this orientation. All right, and let's write down the Cartesian equation for this. That is, let me write down the equations individually. And y equals 3 minus 4 sine 2 theta. And well, we're going to solve for the trigonometric function on each side. So that's going to be 5 cosine 2 theta equals x minus 1, and cosine 2 theta equals x minus 1 over 5. For the y, that's going to be negative 4 sine 2 theta, or not squared, 2 theta. And that equals y minus 3, and sine 2 theta equals y minus 3 over negative 4. Don't worry about those negatives, but recall that when we use the trigonometric identity, that square is going to become positive. And again, I'm going to take that side note we took, or that we covered last time for, well, let me start with cosine. Cosine squared 2 theta plus sine squared 2 theta equals to 1. Recall that this identity, this Pythagorean identity, holds true for your favorite angle. Well, typically we use it for cosine squared plus sine squared equals 1, but it also holds true for theta being, for x being 2 theta, 5 theta, infinitely, I don't know, your favorite function in there. Okay, so we're going to replace cosine 2 theta with their corresponding equations in terms of x and y. So this one will be x minus 1 over 5 squared plus y minus 3 over negative 4 quantity squared equals to 1. And well, I think from here we're almost there. X, actually it's only one more step here. Squared over 25 plus y minus 3 squared over 16 equals to 1. So we have an ellipse, isn't it? Because, well, both terms are positive and they're both squared, and the two denominators are different. And well, notice the denominator of the x is larger than that of the y. That means it's going to extend horizontally, right? Which matches the graph, I think, right? Very well. So, so that's the center is 1,3, which I think it's a pretty good estimate here. And well, there's 5 units and minus 5 units on the sides, 4 units up and 4 units down. So I think this describes very well. Okay, it's very well represented. All right, let's do another one. And for the next one, you might want to be very, very careful. You'll see why. So number 1, let's sketch the curve represented by x equals tangent squared, y equals secant theta within this interval, negative pi over 2 to pi over 2. So in this case, this is our, okay, let me check something real quick. T-min and T-max, all right? So let's label. So whenever you're given a specific range, this means T-min and this means T-max. All right, on your calculator. Okay, and of course we're gonna have a look at the graph, and as well we are going to write this using a rectangular function. Okay, so let's go to our graphing calculator now that we have the window open. So click on window and make sure that you have for the T-min that negative pi over 2. And for T-max, that pi over 2. Alright, and let's go to y equals to type our function. Clear whatever you have in here. And well, so the first one is tangent squared. So tangent, okay, so need to be very careful when writing the square for tangent. So my advice for this is open parentheses, type the tangent function, put the variable, close parentheses for the angle, and close parentheses for the entire function, then square it. All right, so square. For the y equation, the y component, we have a secant, but unfortunately we don't have a secant button for our calculator. So in this case, we're going to use identities. How about 1 over cosine? Isn't that secant? And, oh, hold on. We need a variable here. Otherwise, it's going to be like a mute function. Yes, so let's see. Okay, here's where you don't blink, okay? Don't blink. I think I'm going to need it at a slower motion here. I'm going to go to step 0, okay, 0.001. I need it in a slower motion and graph. Okay, so here is the thing. There is something here. For whatever reason, it didn't work here in my applet here, but you may have seen it on your calculators. Did you see that like a particle bouncing back and forth by any chance? Did you get no? None of you got that part? It did like this. So it first came in this direction. So let me go back to the paper, and I don't know why it's not showing that. It did go back and forth. Okay, so this is what you were supposed to see. So you're supposed to see it's like a curve, of course. And we will figure out what this curve is actually using the corresponding identities. And well, so This is so what we are. Okay, and let me color code this. This is going to be important. So first, and or rather before, and after. So before it's going to do this, it's going to come from whatever, and then it's going to hit the wall, if you will, and then it's going to bounce back to. It's going to bounce back. So for whatever reason, it's not being shown on my calculator this way. I don't know why, but I have the suspicion of why. Let me do something real quick. Let me change the t-step to 0.1. Hopefully, nope. Window. Oh yes, sort of, but not quite. Anyway, so that's what's supposed to happen here, but for whatever reason it didn't show. Now, well, so let's see. In the previous couple of examples for which we had circles and ellipses, we used the trigonometric identity sine squared plus cosine squared equals 1 because that's what we have for circles and ellipses, parametric equations in terms of those two functions. However, we have a new function that involves tangent and secant. So there is another identity, actually it's one of the Pythagorean identities that involve tangent and secant. Does anybody remember which trigonometric which trig ID is that one?
1 over cosine?
1 over cosine, but 1 over cosine, that's just secant. So it's a trigonometric identity that includes both the tangent squared and some secant. You know, tangent and secant. It's involved. Let me give you a hint. So tangent squared theta plus 1 equals secant. Just secant squared, all right? Now, here's the thing. This tangent squared matches the x, all right? But in this case, we have only secant to the first power, not to the second power. So what we're going to do here is, let me rewrite this tangent squared, that's fine, plus 1 equals to secant quantity squared. And okay, let me highlight so you can see how is this going to look like. This is going to be the whole thing, but this one right here, it's going to be just the secant without the square. All right. So tangent squared equals x, simply x plus 1, and in this case secant, which is y to the second power, which is x plus 1 equals y squared. All right, what kind of conic section is that one? X plus 1 equals y squared. It's a parabola, right? And doesn't that look like a parabola? It's only one side of the parabola, I mean not the whole thing, but it looks like, yes?
If you want to see the balance, set the t-step to 0.5.
0.5, did you see the 0.5? Okay, let me see. 0.5. Yeah, but it was
really fast for you.
Yeah, it was really fast. So but it does it. Thank you. So that's a parabola. All right. Okay, so another very important result, well, when it comes to converting between rectangular and parametric form. So another very interesting property about parametric equations is that the way that we parameterize these functions it's not unique. We can find actually infinitely many ways to parameterize a rectangular function. So, okay, like for example, number 6. Let's write a set of parametric equations for the rectangular equation y equals 2 over x or the quantity x minus 1. So, and okay, one way, actually I'm going to write a few. So let's write the system. Well, you can simply say x equals to t, and y will be, well, replace x with t. That's going to be 2 over t minus 1. So now everything is in terms of t's. Alright, so I think this is like the simplest version, the simplest way to write a set of parametric equations. But there's other ways. For example, I don't know, maybe what about x equals t plus 1? You can set x equals t plus 1 if you want, that's fine. Y equals 2 over t plus 1 minus 1, which is ultimately 2 over t. And that's your set of parametric equations. Now describe it in a different way. If you eliminate the parameter, you should get back to the original Cartesian function or Cartesian equation. Another way, I mean, why not? X to be e to the t, well then y equals 2 over e to the t minus 1. That's another way to parameterize this equation. Is there another way? Well, of course. How about x equals the square root of t, y equals 2 over the square root of t minus 1. Alright, but what's the purpose of having different options for these parametric equations? Well, these have to do with the domains that these parts may have, and that those domains will have an impact on when it comes to plotting these functions. You know, for example, the domain of t, well, it's a polynomial, it's all real numbers, that's fine. So that's going to describe most likely like an infinite, you know, well, like an infinite path, you know. Same for t plus 1. But what about e to the t? Well, the e to the t will have some restriction that we will actually see later in the section when it comes to do the same. So because in this case the e to the t never goes to 0, so whatever particle will never reach that 0, as you will see later. Well, the square root of t, well, it includes the 0, but it doesn't include the negative values, right? And well, it depends on the purpose, on what do we want to describe as a path for a given particle, and that depends on our choices of these parametric equations. Okay. Well, so let's write another set of parametric equations for the vertical line, x equals to 4. So number 1, let's draw the graph of the vertical line. At 1, 2, 3, 4. Well, so that's our graph. And x, well, x equals to 4. Okay, what would be a good equation for y? Okay. So, do you notice that it doesn't matter? Okay, so it doesn't matter what value of y do you choose. X is always 4, isn't it? So, how can we represent that any value of y? Just t. Any value, or t squared, or I don't know, t cubed, t to the 17, t to the 29, your favorite exponent. So any number. All right. Now on another kind of situation, so we are asked to find a set of parametric equations for a line, in this case, that in particular passes through 2 points, 1,5 and 3 and 3,2. So we're going to do a lot of this in Calc 3 next semester. So when it comes to defining these parametric equations to find integrals, derivatives, find directional derivatives, gradients, and a lot of pretty fun stuff that it's applied a lot in like computer science, in the science of video games, like knowing trying to find points of certain slopes, certain slantiness, you know. So we need to know those slopes in the 3D system, and we need to describe this in terms of parametric equations. Well, you will see that. Okay. Well, so of course we're going to start with the simplest case of parameterizing an equation, which is the equation of the line. So number one, let's see. Number one, we might want to write the equation of the line that passes through these 2 points. Of course, we have enough information, and ultimately we need the slope and a point. We don't have the slope, but we have 2 points. We can find the slope by finding the slope, so that's 2 minus 5 over 3 minus 1. So that's a negative 3 over 2, which is negative 3/2. Alright? And we may go ahead and write the equation of the line y minus y1 equals m times x minus x1. That's the point slope form. And well, so just plug in the numbers, the slope of negative 3/2, and choose your favorite point. I mean, I'm going to use the first point, the 1,5. So y minus 5 equals negative 3/2 x minus 1, and y minus 5, that's going to be negative 3/2 x plus 3/2, and then just solve for y by adding 5 to both sides. So y equals negative 3/2 x, and 3/2 plus 5, I get 13/2. So that's the equation of the line, for which we might want to do a parametric equation. Now, one important thing here is the following. So when it comes to interpreting the slope, recall that the slope is the ratio of the rise to the run. That means the number in the numerator is the change, or this describes the change in y, and the number in the denominator describes the change in x. All right? So that's what we are going to have. And let's label this as a B, and let's label this as an A. And well, in this case, I'm just going to give you the formula to do this parametric representation in general for y equals mx plus b. Or simply mx plus b is represented by at, or rather x equals at plus y1 x1, and y equals bt plus x plus y1, where in this case, think of having the slope as split into the x and the y, so that's what we are going to incorporate here. Alright, so in this case, negative 3/2 x plus 13/2, using the formula. All we do in this case, well, x equals a, which is the change in x, that's a 2, t plus x1, and well, in this case I'm choosing the first point as to have the x1 and the y1 respectively, so that's going to be plus 1, and y equals the b value that comes from the slope, that is the change in y. But be careful, because I already used a positive number, then we need to use the negative number in this case. 3t plus y1, where's the y1? In this case is 5. All right, and that's how we parameterize a linear function. And we're going to do a lot of this again in Calc 3. All right. And well, if you want like a generalized way to, without even finding the equation of the line, so you can just use this formula: x2 minus x1 times the t, and y2 minus y1 times t, and of course plus x1 and plus y1 respectively. You can just put that on your notes, on your sheet of notes for the final exam, and there's really anything crazy to go about this, right? So. All right. So now using the formula right here, the formula that we have in the green box right here, let's find a set of parametric equation that goes through these 2 points. And well, you might want to label. Why not? Label them. This is x1. This is y1. This is x2. And this is y2. So the set of parametric equations is x equals x2 minus x1, t plus x1, and y equals y2 minus y1, t plus y1. And well, this follows to x equals to, okay, x2, which is 10, minus x1, and be careful with the negative signs, right? Because that's going to be 10 minus negative 8 t plus x1, which is negative 8. Be careful with signs here. And y is going to be negative 5 minus 1. Yeah, there's a lot of negatives going on here. T plus y1, which in this case is 1. All right. So let's just clean up the parentheses and the negative sign. So that's going to be 10 plus 8. That's 18. 18t minus 8 on the one hand. And for the y equation, it's going to be negative 5 minus 1, negative 6t plus 1. So that's the set of parametric equations, of linear equations that actually pass through these 2 particular points. So in this case, we are not just finding any random set of parametric equations that look linear. That is, they have the powers of t are 1, right? So in this case, yes, the variables have a power 1. But in this case, we're finding a particular set that passes through those 2 points. That's what we're doing in this study. All right. Okay, so another typical situation in parametric equations is to find a very particular parametric set of equations that satisfies a condition. Number 1, well, it's a parabola y equals x squared plus 3, but in this case at t equals 2 and contains the point 1 comma 4. All right, so of course, let's first of all do the incorrect answer. So in this case, we have y equals x squared plus 3. All right? And x, of course, x can be anything. Pick your favorite, the simplest possible. Let's call it t. All right? For this reason, well, this really becomes t squared. However, is it true that at t equals to 2, we have the point 1 comma 4? Let's verify that first. So for example, so x equals 2 and y equals 2 squared plus 3, that's going to give us 2, and 4 plus 3 is 7. No, we have the point 2 comma 7, so we need to parameterize the equation in a different way. How can we do that anyway? Well, maybe you might want to try other, like shifting the x or doing anything else sort of crazy, if you will. Okay, so indeed, let me cross this. This is not correct, all right? And I'm leaving this just so you can see what it's not supposed to do or to be done. Okay. So how about shifting x equals, I don't know, t minus 1? Okay. Then plug in y equals quantity t minus 1 squared plus 3. Now, plug in t equals to 2. So at t equals to 2, x equals 2 minus 1, and y equals 2 minus 1 squared plus 3. Oh, yes, this is 1. This is 2 minus 1, which is 1, squared, which is still 1. 1 plus 3. And this is the 1. All right? This is the right choice. So in some cases, we need to do mini or slight tweaks in the system in order to fit certain conditions that in this particular case, that when t equals to 2, the particle is at a given point. All right? So let's see. All right, so now let's analyze the set of parametric equations right here. All right, so the thing here is that each set gives the same function when eliminating the parameter. But we are going to describe the differences here, which is what I was talking about before, that depending on how do we describe these parametric equations for the same function, you know, it's going to depend on the purpose, of course. All right, so number one, how about we go to our graphing calculator and plot. Let's plot the four of them, well, one at a time, of course. So it's t cubed and t. And then, well, so if we graph, I need the window to be, I'm going to go from -10 to 10. These ones are no longer trigonometric, so no need 0 to pi or anything like that. So let's graph. And it was too fast, I needed a little slower. Window maybe 0.01. Okay. Okay, so hopefully you didn't blink. Hopefully you noticed that it went from left to right. All right? Okay, let's draw the graph, indicating that with arrows. And just indicate the direction with arrows like this. All right? So, well, let's eliminate the parameter to find out what's the function that it's being described. Well, from the second equation on the system of parametric equations, we have that y equals t. So if x equals to t cubed, then we can replace t with y because of the second parametric equation. That means x equals y cubed, and solving for y, we get y equals to the cube root of x. All right? And well, if we consider the domain of the function y equals the cube root of x, it's all real numbers. We can take cube roots of positives, even negatives, and 0, as opposed to radicals with even indices like the square root, the fourth root, the sixth root, etc. We cannot take roots of those numbers. So in this case, you might want to be precise with the domain. So domain, it's all real numbers. It's important to take that into consideration. Well, and now let's go about the second set of parametric equations. So, and in this case, notice both components, both equations have opposite signs. So, how about we go to the graphing calculator and see what's going to happen this time. Okay, so I'm going to go to y equals, second insert, I'm going to put a negative, second insert, negative. All right. Make sure your parametric equations look like this. And by the way, be very careful. Recall that your calculator has two keys right here for negatives. Number one, the one in parentheses is the one that you want to use to have a negative sign at the beginning of a term, because otherwise the other negative is to subtract two numbers, and that one goes in between two terms. So be careful, because otherwise if you put this one instead, you are going to get a syntax error. Okay, so let's graph and see what happens. Same graph, but what's the difference this time? It went from right to left this time, right? So, same graph. And yes, even though I'm going to draw it again this time from right to left, well, that doesn't tell me anything when someone else sees it. So I need to draw arrows to distinguish that. Alright. And well, of course, we have a graph whose domain clearly is also all real numbers. Let's eliminate the parameter again. And well, from the second equation, we have that y equals to t, or rather negative t, x equals t squared, or rather cubed, x equals negative, from here, from this one, yes, this is going to be t equals negative y, and I'm going to replace this with negative y cubed, and well, I'm going to take the cube root, and don't forget this negative also. I'm going to cube first. Okay, be careful, because this one is going to be negative. Y cubed is still going to remain negative, but times the negative in outside of the parenthesis is going to become positive. And well, that's the same function, cube root of x, whose domain is also negative infinity to positive infinity. But in this case, the particle travels from right to left as opposed to left to right from the previous case. Okay, let's have a look at the third version of this parametric equations. Well, so okay, let me make some space. And so let's type this in the graphing calculator. Clear. And well, the first equation, that's a t raised to the 3/2. And the second is y equal to the square root of t. Second square root of t. Alright. Let's see. Okay, let's graph. But again, don't blink. And it's going to go from left to right. Alright. So it's very similar to the first two graphs that we had, but in this case, the difference is that we are only seeing the right side of the tail of the graph. We're not seeing the left tail. Any ideas of why is this?
Using the square root.
We have the square root, right? So the square root function on the y equation has a restricted domain, right? Can we plug in any value of t at any time, even negative times? No, that's why we're only dealing with positive times. So, and in this case, including 0 in particular, be careful, okay? It includes, exactly. So we're going to draw the graph. And in this direction, in the same direction as in part A. And I'm gonna draw a solid bubble at the origin for a big purpose. You'll see why. And of course, let's do the same. Eliminate the parameter and describe the equation. Okay, so in this case, from the parametric equations, y equals the square root of t. Okay, but in this case, let's solve for t, which is going to be y squared. And then, well, from the equation x equals t to the 3 halves, replace t with y squared, x equals y squared to the 3 halves. See how the 2's cancel? That's going to leave us with x equals to y cubed, which is the same as y equals to the cube root of x. Alright? Isn't it the same function as in parts A and B? But there's a little difference that we need to specify in this case, because I mean, if we were looking at a paper, the function y equals the cube root of x, okay, no problem. The domain of y equals cube root of x is all real numbers. But in this case, we know for sure that this cube root of x comes from this parameterization. This cube root of x is coming from a different parameterization, which is the same graph but having a particle going in different direction. In this third case, we have, yes, this same cube root of x, but in this case it's a different parameterization, but in particular, this parameterization has a restriction. Alright, so when we write the domain, from 0 to infinity. Not all real numbers. Alright? Let's do the fourth case. Oh, we have exponentials. That doesn't even look like we're going to obtain the same equation, but you will be surprised. Okay, so let's see what happens. Let's type the equations. And so e to the negative 3t, so second ln, negative 3t, and e to the negative t. Okay, so be careful here. Okay, number one, this time it's coming from right to left. It's the same graph as in part C. Alright? It's very similar. It's pretty much the same, if you will. But in this case, one of the main differences is the direction that the particle is traveling this time. And well, let's see. Number one. Okay, let's eliminate the parameter and then we talk about the restrictions for this set of parametric equations. So we know that y equals to e to the negative t, alright? And we have that x equals e to the negative 3t, which is the same as saying e to the negative t quantity cubed, alright? I think that if we write it this way, it's easier to just go back and replace this e to the negative t with simply y, which is going to give us x equals y cubed. Isn't it the same? Isn't it the original function? Y equals cube root of x. Now, but what would be the restrictions in this case on the domain? And be very careful with this one.
Is there an activity to both open?
Both open. How come both open again?
Because you can have the, if you plug in t to 0, it's supposed to be infinity.
Well, in this case, actually, the reason is that the exponential never goes to 0. Alright, for example, if you try to set this equation, e to the negative t equals to 0, okay, take ln to both sides and good luck, right? Yes, this is negative t, but what's ln of 0? Well, undefined in this case. Well, in terms of limits, it is a negative infinity, but because in this case we're talking about actual values, evaluating functions, well, in this case, functions are defined or undefined as opposed to limits that do exist or do not exist, right? And in this case, well, the function is undefined at 0, or the exponential never goes to 0. Well, so for the restriction, the domain is 0 to infinity, but in this case, excluding the 0. Now, what's the effect on the graph? And this is the reason for which I put a solid bubble on case 3. For case 4, we need to have with this open bubble. Alright? And again, the reason why I mentioned a couple times be careful with this one is because graphing calculators, yes, they're really smart devices, but they're not that smart. Unfortunately, graphing calculators never show the vertical asymptotes and never show those removable discontinuities, namely holes, you know. They don't show those symbols as holes. So in this case, we have to take into consideration all the aspects we know about exponent, or in general, all the functions that we're dealing with. But in this case, in particular, the fact that the exponential function never touches the zero. So now, as you can see, for example, let's say you are in charge of designing the path of a drone, for example. You know, so let me pause this.